A ij uj, which leads to xj equals A tilde ji xi prime. Okay, so you are, as I said, you are in the same, you are dealing with the same vector. So you are dealing with the same vector x, but maybe the vector x when written in the old basis looks like this, and the vector x when written in the new basis looks like this. So you are with the same vector. Okay, but when I wrote this, then you have a operator t which acts on an element. So consider this is a vector space, it has an element x and many elements, and then element y and many elements. So there is a t which acts on x and takes you to y. Okay, so t is actually an operator on the vector space. Again, t has the right to be said as an operator in the vector space V. Why? Because t acts on the elements of vector space. Okay, so t is an operator in V because t acts on its elements. Now it can so happen that there is a group of such t, say t maybe um, t1, t2, and maybe some finite number of operators are there who are acting on V. And if these operators form a group, then we say that this set of element which contains a set of operators that act on vector V, they form a group. Now for example, if they form a group, we say that, hey, look, if you have operator T, you act it with T1, and somehow you get T2 which also belongs to G, and so on. Okay, so T is actually a group operator if it belongs to some set which forms a group. Okay, so we are assuming that we are working with a group of operators acting on V. So I can rightfully say that my T is an operator, is a group operator. I can say like that. Okay, next interesting thing that I would like to comment is, what is the matrix representation of T if we are using orthonormal basis set? So matrix representation of T in orthonormal basis set. Now why this is important? Because you will see that the matrix representation of T in orthonormal basis set takes a very simple formula, and because it takes a very simple formula, hence we try to, or whenever we work with a vector space, we try to form an orthonormal vector space and work with it. So this is what you might have heard in quantum mechanics, that we are continuously working with orthonormal basis. Why we are working with orthonormal basis? Because things are very simple with orthonormal basis. For example, um, remember the vector, the basis u1, u2. So this is the old basis, and this can be written in a very interesting way. I just change notation and I can write this basis in this way. Okay, so if I write in this way, then don't get confused. These are just bases written in a different way. Okay, so if the u1, u2 that we considered form an orthonormal set, then the beautiful thing is, whenever you have u1 and u2 dot producted, you get 0, and whenever you have u1 and u1 dot producted, you get 1. So this is a very simple thing that is going to help you to form a matrix representation of T in a very simple way. Let's look how it is possible. So consider, um, so what is T? As I said, there is some y which you get by acting T on X. and let y can be written as yi ei. Let me put like this, and ei are nothing but the ui. Sorry for the change in notation, I could have written ui. Okay, let me write ui, that would be better. Okay, so ui. So if we are dealing with a 2D case, then what should we do, right? Y is equals to y1 u1 plus y2 u2. Anyways, so y can be written in this way. Now what is x? Now x can also be written as xi ui. Now remember, x and y, they belong to the same vector space, and we are using a basis in the vector space. So I can write y in the basis and x in the basis, the trivial thing. Now the whole formula y that we get by acting t on x can be written in the following simple way. So you can write as yi ui equals t acting on, say, xk uk. Okay, that implies both sides, if I operate with ui, so ui, now what is yi? Yi is a simple number, so I can just take yi outside. This side here, xk is a simple number, it goes out, but ui and the t and the uk, they remain. Now on the left hand side, yi goes out and you just get 1. Right hand side, xk stays out and you get ui t uk. Now if you look at this thing, don't you see that this is as if you have yi and some matrix tik, because now the operator becomes a matrix because of this thing. You can form elements of the matrix also, and you get xk. So you see that if you have an operator, then you can easily form the matrix representation of the operator very easily if you have orthonormal basis. All you have to do is act basis from the left and the right. So let's look at the elements. So whenever I say that ui, was it ui t uk is tik, it means that the t has now taken the form of a matrix whose elements are t11, t12, t21, t22 if you are working in 2D. So we are always sometimes taking examples of 2D so that things go simple. Now what is t11? T11 is nothing but the first basis here and the t operator here and the first basis here again. Similarly, t12 is the first basis here and the t acting on the second basis, and so on. So this is the beauty of working with orthonormal basis set. So what sometimes we do, so consider you have a vector space V and you are given a basis set in V, then there is a way called as Gram-Schmidt or orthonormalization, some name like that. What it does is that if you have a given basis, then you can, using this you can find another set of bases who are orthonormal, such that these are all orthonormal bases. So there is a procedure called as Gram-Schmidt or orthogonalization or something. You can read it up. It takes these vectors, because these bases are also vectors, and it takes a set of vectors, and using those set of vectors, it will give you another set of basis vectors who are orthonormal to each other, and thus everything becomes easy when you do work with operators, finding the matrix representation, etc., etc. Okay. So this is the end of what I wanted to say about linear vector space, and now we jump to our group ideas. So now we will talk about reducible and irreducible representation in further detail. Reducible and irreducible representation. Okay, it's not a difficult concept, it's a very simple concept, and the concept goes as follows. So how should I start? Okay, let us start in this way. So remember from the very definition of reducibility and irreducibility that we did before, I said that if you have a set of operators, or if you have any operator R, say R is an operator and say it's a group element, okay, and we saw that if you choose certain bases, then you can form different representation of this operator. So if you choose one basis, so you get say one-dimensional representation. If you choose two bases, maybe you can get two-dimensional representation of the same operator. Now, I also said that you can also form a higher dimensional representation of R in a very simple way, that if you just write this representation here and put 0 here, and this representation here, then this can form a three-dimensional representation of the same operator. Why three-dimensional? Because the first one, D1R, is one-dimensional, so it will have only one element, so one dimension, and D2R turns out to be 2 cross 2 matrix, so overall it will become 3 cross 3 matrix. Okay, so if D1R is 1D and D2R is 2D, and by 2D these are nothing but matrices. Okay, so this is an idea, and there is a simple name. We say that, hey, look, we formed another representation of R by using two different representation, and we can say that I used one representation and I formed a direct sum with another representation, and I formed a new representation. So when you look at this weird mathematical stuff, remember that we are actually doing this. That's clear. Okay. Now, sometimes what happens is, so sometimes it so happens that you have some representation of R, but it looks very complicated. It may not be as simple as given above. Okay, so it can be a complicated matrix. For example, say that R is a group operator, and you formed a 3 cross 3 complicated matrix representation of R. Why it's complicated? Maybe you ended up with a basis that gave a complicated matrix to you. It's your fault that you worked with a bad basis. Okay, now the question is, if I say that d prime R is reducible, if I claim that, hey, d prime R is reducible, it means I'm telling you that, look, you have a complicated matrix which is a representation of R, but you can always find the, but you have a similarity transformation which, when acts on this complex representation, and I remember when I said similarity transformation, it meant going from one basis to another basis. So I said there is a similarity transformation by using, oh, okay, let me not use T because we used T for some other stuff. Okay, let me use S. So there is a operator, there is a matrix S, which when acts on this in such a way, there should be inverse, maybe in this way, then the complicated matrix turns out to be very simple. There is some element here, and there is a 0 here, there is a 0 here, and that turns out to be some element here. Then I say that, okay, since I was able to find such a similarity transformation that formed a simplified matrix of this form, which is diagonal, I say that d prime R is completely reducible. Okay. So this is the whole idea when people say that, hey, do you have a reducible representation of a group? You say that, okay, so I have a group. That means I have a set of operators, and these operators can be formed, can have matrix representation depending on how they act on the vector elements. And depending on how they act on the vector elements, I can use the basis and I can form a matrix representation of these group elements. But sometimes if you choose a bad basis, you form a very bad matrix representation which looks a complicated transformation. And you are lucky sometimes, not you are not always lucky, but sometimes you are lucky that you find some matrix X that changes your complicated representation of the group element to a very simple representation of this form, it's of diagonal form. Then we say that, okay, so d prime R, which was a representation of group element R, is completely reducible. Okay, fine. So let me put it in another way. We are going to discuss it in a different way. The way is the following, that um, so consider you have some group elements and you are forming a three-dimensional representation. So consider you are forming a three-dimensional representation of a group element R. So and you were lucky and you found a representation of d of R which was in this form. So there is AI, BI, EI, CI, DI, FI, and there's 0, 0, G of I. So you found a matrix three-dimensional representation of some group operator, group element R, and this is a 3 cross 3 matrix, and you found a very good representation. But you saw something very interesting. You saw that this turns out to be very interesting because if you do put a line here and you put a line here, then something interesting happens. You'll say, what interesting thing happened if I just put a line here and I put a line here? Well, the interesting thing that happens is the following. Um, okay, so let me write it as Ri. So this is the Rith element. Now what happens if I multiply dr1, so R1 is an element of the group, and dr2, so R2 is also element of the group, I should get dr3, and dr3 should be of this form. Now if dr3 is of this form, then I can happily say that, okay, everything is good because the representations, they also follow the group algebra. So when you do this multiplication, so you take 3 cross 3 matrix and another 3 cross 3 matrix and you multiply them. So I'm just writing, oh, let me write it then. So if you use A1, B1, E1, C1, D1, F1, 0, 0, G1, and then you multiply with A2, B2, E2, C2, D2, F2, 0, 0, G2. So let's see, what do we get? The first one, I'm going to get A1, A2 plus B1, C2. And here I'll get A1, B2 plus B1, D2. And here I'll get A1, E2 plus B1, F2 plus E1, G2. Here I'll get C1, A2 plus D1, C2. here I'll get C1 B2 plus D1 D2, and here I'll get C1 E2 plus D1 F2 plus F1 G2. Here I'll get a 0, here I'll get a 0, and here I'll get a G1 G2. Now look at the beauty of this matrix. It's the same. Yes, it belongs to the same object, because here you have a 2 cross 2 matrix, here you have 1 cross 1, and it looks the same as the old matrix. So the new one, I can happily say that the new one is yes. It must be some, there must be some R3, and whose representation is this, because it turns out the representation of this matrix under multiplication is same as when you multiply the two matrices and everything. Then sometimes, so you see that there was a group of elements, and you were happily, and you were very lucky that you found a basis such that your group elements have a 3 cross 3 representation which is as simple as this. Now why should I say this is as simple as this? Because the matrix AI, BI, CI and DI, they form the two-dimensional representation of R, and the last one where you have G1 G2 multiplication, turns out it is one-dimensional representation of R. But sometimes you can be very unlucky, and you may not find such a beautiful representation as above, such that the representation that you got above 3 cross 3 gave you a hint that look, you also have a two-dimensional representation, that is a 2 cross 2 matrix of the same group element, and you have a one-dimensional representation. So sometimes you can be unlucky and you can get again a complicated representation of R. So it turns out to be some D of R, which is very complicated. And then if you are lucky, you get a similarity transformation, and if you get a similarity transformation that brings your matrix in this form, then we say that D prime R is reducible, not completely reducible, but approximately reducible. So instead of writing approximately reducible, I just write reducible. That means if I can find some matrix S which when acts on this complicated representation, it gives you some 2 cross 2 matrix here, and some matrix here, a 0 here, some 1 cross 1 here. Then you say that, okay, so D prime of R is just reducible, not completely reducible. If A is 0, if this element here it turns out to be 0, I mean all the elements here turns out to be 0, then you say that it's completely reducible. Else you say that, okay, it is reducible, not completely, but okay, fine, we can deal with it. Okay, any doubt till now? I would like to hear a no from both of you, then I will proceed. If you have any doubt, you can ask, because this is a very important concept that I'm discussing.
Sir,
if you want me to explain.
Yeah, from how can we get that metric S and S inverse?
Yes,
Yeah.
yes, that's a later discussion.
Okay.
But the question is, if you can find some S like that, and how you make the S, we will do that in the future lecture. But maybe you have, maybe if I give you a method and you really find S, and then you say that, okay, the representation D prime of R is a reducible representation.
Okay.
So when you say that you have reduced a representation, that means here the elements will form a lower dimensional representation, and the elements here must also form a lower dimensional representation of the same group element. So whenever something is reducible, that means the elements on the diagonal side, they are somehow the elements there will help you get a lower dimensional representation of the same group element R.
Okay. And one more thing, sir.
Any doubt?
Yeah. So when you do these operations, S into this matrix D prime of R and again S inverse, then we always get this diagonal elements only, or is there any
If you get
possibility?
diagonal, then you
Yeah.
say that D prime of R was completely reducible.
Okay.
But if you don't get diagonal and there is some A there
Okay.
which lurks inside, then you say that okay, it is just reducible, because anyways the A is not disturbing you much, and the elements in the diagonal, they also form lower dimensional representation of the group element. So
Oh,
you
okay.
can be a little bit happy with that, and you can say that it is reducible.
Okay.
Okay, any doubt, Alham?
No.
Okay, so to make things complicated, just to make things complicated, so if it's just unnecessarily I'm making it complicated, if D of R was an n dimensional representation of a matrix element R, and it turns out that you were able to break D of R, D prime of R by some transformation, and using the transformation you get D of R, and D of R was very beautiful. It turns out to be some D1R and some A and some D. Okay, let me write it Dm here, and let me write n minus m R. If I write it like this, what do you see? You see that dmr is an m cross m matrix. So dm of R is an m dimensional representation of R, and the lower one is nothing but n minus m cross n minus m matrix, which is dn minus mr. And you say that okay, you have n minus m dimensional representation of the same group element R. Okay, this is some mathematical stuff that you'll find in books, so I just mentioned it for simplicity, so that when you read there is no issue. Okay, but we understood everything about the matrices and similarity transformation, blah blah blah. But now the question is, we have to discuss the whole thing in terms of vector spaces. So we have to talk about reducibility and irreducibility in terms of vector spaces. So we just discussed in terms of similarity transformation and here and there, but we didn't talk about vector spaces. So let's talk about vector spaces. So if you had a complicated representation of a group element R in say 3 cross 3 matrix representation, that means you used a vector space V who had 3 bases, because it's a 3-dimensional representation, so there was basis E1, E2, E3. It turns out that if the vector space V can itself be written as a direct sum of 2 other vector spaces, then this one gives you a hint about the fact that look, D of R D prime of R can be reducible. That means if this one was formed in a representation V, and it turns out that V has 2 sub vector spaces, V1 and V2, And we all know that if you have sub vector spaces, then how you can make a direct sum of vector spaces and form a larger vector space. So if the reverse happens, that D prime of R is a matrix representation using V, which is a larger vector space, and it turns out that your larger vector space can be broken down into two subspaces, then it's a clear indication that you should find the matrix representation of the group element R in the vector space V1. Say V1 is one dimensional, then it's a clear indication that you should find a one-dimensional representation of R, and say V2 is two-dimensional, then it's a clear indication that you should find a representation of R, matrix representation of R in two dimensions. So this is another way to find out whether your representation is reducible or not. It all depends on the vector spaces that you have used to form the complex representation of R, which is the prime of R.
Excuse me?
Any doubt? Mm-hmm.
If we have sub vector spaces like V1 and V2, is it always possible to
No, not all
decompose the
vector
matrix?
spaces. No, not all vectors can be decomposed in this way. Not all vectors.
No, if the vector space is decomposed.
Yes, then it's yes. Then I would say that yes. If the vector space is decomposed, that means that the prime of R will have can be reduced to a representation such that the top whatever exists at the top corner is going to be a representation in V1, and whatever exists in the lower corner is going to be representation in V2, because we always do representation using the basis in the vector space. So whenever we talked about going from one representation and to a reducible representation, we should keep the idea of vector space in the back of the mind. That's why I gave you this explanation. Okay, no doubts now. So in mathematics book, you will find this thing written. If you have a vector space V, which is from I equals to 1 to K, and it decomposes into K subspaces, that means D can be written as a direct sum of so many representations. So let me put a direct sum symbol here and a direct sum symbol here. Direct sum, direct sum, direct sum here, and lambda I. Did you understand this mathematics? Is just complicated representation if you have so many things at hand. I'm always doing in 3D, 2D, 1D for simplicity, but in general, if your vector space turns out to be broken down into many vector spaces, V1, V2, say Vk. Okay, similarly, the representation of R can have reducible representations and so on, so on. Okay, so what did we learn? We learned that if you know reducible representation of a group element R, then you can always form a new representation by direct sum of the old representation, and this will also happily turn out to be a good representation of the group element R in higher dimension, because when you do the direct sum of the matrices, the dimension increases. So if this is one dimensional, this is two dimensional, then the overall matrix here you get a 3x3 matrix. So you have formed a three-dimensional representation of group element R. Or yeah, that's it. Okay, simple. Okay, so this is all about reducible and irreducible representation. Now, what we should do is we should actually study an example for simplicity, but Let me see if there is suitable example in my notes, so that because we talked about the transformation, and we talked about the operator T in one dimension, right? And I want to give you an example in two dimension. So let's do an example that would be better. We have it one. So this example is going to remind us about the old concepts also. So whenever we talked only about um, um, remember when we talked about, okay, we have psi of x and psi of minus x, let they be the basis, and we constructed the matrix representation of I and matrix representation of operator E. We did it like that, remember? So this was all in 1D. Now just to explain this, let's take an example in 2D. And the question is that consider you have a rotation R that creates you have an operator R that creates a rotation, and R acts on coordinates. Then I'll give you four bases. Psi1 is equals to x square, psi2 is equals to xy, psi3 is equals to y square. Okay, I'll give you three bases, psi1, psi2, psi3, and I ask you, what is the matrix representation of operator R, such that first you have to talk about operator P of R, which acts on size. So remember, whenever we saw that an operator T was acting on the coordinates, we talked about an operator OT which act on the function, and then we found the matrix representation of this. Okay, so remember the step. So the same thing we'll do. We know R that acts on coordinate. We formed P of R that acts on functions, and whenever it acts on certain function, we are going to write it as a linear combination of all other bases, because psi1, psi2 and psi3 are bases. So similarly, we do PR act on psi1, P2 act psi2, and PR act on psi2, and PR act on psi3, and there is same linear combination, and this linear combination later will help you form a matrix, and this matrix turns out to be the matrix representation of P of R. So this will give you the matrix representation of P of R, or in a more better way, matrix representation of R, not P of R but R. Okay, so let me remove it. This is our representation. So now question is, how R acts on coordinate? That's the important question. So I give you an example. So consider R is 1, 0, 0, minus 1. Okay, so how does it act on coordinate? So when R acts on the old coordinates, you get the new coordinates. X, Y are the old coordinates, and you get new coordinates. Okay, so the basis that you have seen above is in old coordinates X and Y. So let us write everything in the new form, or we can do something else. Okay, how about let this be a homework for you, and find the representation D of R, and then we discuss it tomorrow. Let's do it in that way. Okay, so let's end the class here.